Janes, that works for Ross SPA, and he's going to talk about the energy savings in the modern buildings through the application of polyvalent, if I'm pronouncing it correct, heat pumps with simultaneous and opposite loads.
So, good afternoon, ladies and gentlemen. I would like to give you a warm welcome to this presentation, which is focused on the polyvalent heat pumps technology. In particular, we see some applications with simultaneous and opposite loads. This presentation will have an introduction just to define the context of the energy efficiency in the modern buildings. We will then have a look at the operating principle of polyvalent heat pumps. We will see a real case application in a full bank system, and we will draw our conclusion. First of all, I would like to spend some words about the context of the energy efficiency in modern buildings. So nowadays, tertiary development is focused mainly on large windows facades, light walls, and low thermal inertia. And this leads to a high flexibility required in the destination of the rooms, especially if you need to rent the spaces or if the building is certified as a core and shell, for instance, with the LEED certification. And discretion is left to the tenants to define the interiors. In this situation, there is an increasing grade of indetermination in the cooling and heating loads. More and more in the modern buildings, air conditioning is required all year round. So a certain amount of cooling is required even during winter time. And this leads to the presence of simultaneous and opposite loads. How can the HVAC equipment then help to improve the energy performance of the building and also make the building more valuable, to increase the value of the building? Well, we know the chillers and the HVAC system in general, they are the single largest user of electricity in most commercial and institutional buildings. And in many cases, they are the single largest user of any form of energy in the building. So, if we can improve the efficiency of the HVAC system, we can significantly improve the energy performance of the whole building. The independent production of chilled water and hot water, which is usually the traditional system made by a chiller and a boiler, is not always the best solutions in terms of energy efficiency. And this is particularly true in case of a building with the simultaneous and opposite loads, which can be, for instance, a multifunctional building where we can have a hospital with a hotel, a shopping mall, a fitness center, and so many different destinations of the spaces with different requirements at the same time. And in this case, the sources of chilled water, which are usually the chillers, or hot water, which are usually the boilers, or could be district heating, or whatever is available on site, they do not interact with each other. So they do not allow to achieve some important savings which could be possible. A polyvalent heat pump is a heat pump equipped with a versatile heat recovery system which can provide the following functions: cooling only, cooling and heating at the same time as the free heating, or heating only, with simultaneous or independent production of chilled water and hot water according to the system requirements, in order to match the requirements of the plant system all year round. The switch between the operating modes is completely automatic and depends only on the requirements of the building or on the spaces to air condition. Now, without going too deeply into the technicality of the system, because different manufacturers can have different, let's say, solutions to achieve this result, now I want to spend some words about the operating principle. If the building requires only cooling, then the unit will run as a normal chiller, simply removing the heat from the spaces that need to be cooled and rejecting the heat to the atmosphere or to the water in case of a water-cooled unit. But the heat rejected could be recovered to produce hot water if we have a simultaneous requirements of chilled water and hot water. In this case, we can say that we simply remove the heat from the rooms that need to be cooled and send this heat, transfer this heat to the rooms that need to be heated. And in this case, we have a double useful effect with a single power. If the system, the plant system, reaches the set point in cooling, but we still have requirements of heating, the unit automatically turns into a heat pump, recovering the heat from the air or from the water, and rejecting and producing hot water for the spaces that need to be heated. The hot water can be produced to the heat recovery or to the main heat exchanger. The simultaneous production of chilled water and hot water in the total heat recovery mode allows to increase the global efficiency of the unit. Maybe you are familiar with the concept of ER, energy efficiency ratio for a chiller, which is the ratio between the cooling capacity and the power input used to have this cooling capacity, or the COP for a heat pump, which is the ratio between the heating capacity and the power input used. In this case, we have the simultaneous production of cooling capacity and heating capacity. So the manufacturers and insiders use the TER, total efficiency ratio value, which is the ratio between the sum of cooling and heating capacity in a specific operating conditions and the power input used to obtain this. This is the typical trend of a TR value for a polyvalent heat pump, let's say rated at 550 kilowatt, working in a mid-season situation, so 15 Celsius ambient temperature, producing chilled water at 7 and hot water at 45 Celsius. We can see that when the cooling and heating loads are comparable, so both 100%, both 75 or 50 or 25%, the TR value reaches its best values. This is the reason of this is that in this case we can recover all the heat produced by the unit to produce hot water. So in this case we have a really double power input with a double useful effect with a single power input. When the cooling and heating loads are unbalanced, it means that we need more cooling than heating, or we need more heating than cooling, then in this case the TR value is lower. The reason is that if we need more cooling than heating, then it means that a part of the heating capacity is rejected and cannot be recovered. Or if we need more heating than cooling, it means that part of the heating capacity must come from the heat pump. And so we have to pay for that. We have to use additional energy. But in this situation, in these operating conditions, TR values of exceeding 9 are not uncommon. It means that we pay 1 to get 9. So we get 9 kilowatts of cooling and heating capacity with just 1 kilowatt of power input. What is the typical application of this technology? Well, polyvalent heat pumps can be used in 2-pipe and 4-pipe systems, which means hotels, hospitals, shopping malls, office buildings, but in general all applications where simultaneous or independent production of chilled water and hot water is required. Even a process cooling application could be used, or the industrial applications as well. This is the typical, let's say, a principal arrangement of a 2-pipe system where the main heat exchanger is connected to the air conditioning system and is producing chilled water in summer and hot water in winter. And the heat recovery is connected with the domestic hot water circuit and can be used as hot water to produce domestic hot water. This is the principal arrangement for a 4-pipe system where we need only space cooling and space heating. And in this case, the main heat exchanger is connected to the space cooling circuit, the heat recovery to the space heating circuit, and simultaneous or independent cooling and heating are possible. Now let's have a look at a real case application. This is a refurbishment project of a 40 years building in Milan, completed in 3 years ago, in the year 2011. The building was enlarged from 4 to 6 stories, and the layout of the building was completely renovated. The investors wanted to achieve the LEED certification, gold level, according to the LEED Guide, Building Design and Construction version 3 of 2009. One opportunity to achieve this certification was to replace the existing HVAC system made by a chiller and a boiler with a polyvalent system, using only a polyvalent heat pump for cooling and heating. So the building was rated with about 550 kilowatt cooling capacity at 7 Celsius chilled water, and around something more than 400 kilowatt heating capacity with 45 Celsius hot water. A polyvalent heat pump, air to water, 2 independent circuits with screw compressors was used, and the whole system was made with fan coils and independent units using brushless fans. This is the energy modeling of the building in Milan across the whole year. As you can see, a small amount of cooling is required all year round. The reason of this is that this is an office building with server rooms, with very high internal loads in terms of spotlights, crowded spaces, plasma screens, very strong insulation due to the large glazing of the window of the building. And this is the temperature profile in Milan. So how many hours per year we have at different temperatures. Temperature in Milan ranges from -5 to +35 Celsius all year round, which makes the use of a heat pump all year round economically convenient. A life cycle cost assessment made to understand if the polyvalent solution could be the right solution for this building gives these results. All the figures are calculated considering interest rate, inflation rate, and electricity and gas costs, which were in force in Italy at the time that the building was designed. So, in front of an increase in cost for installation, equipment cost of around 30%, considering the saving that we can have in electricity or gas, actually the system is gas and oil free, we can say that in the operating costs we can save around 25% per year, which makes the payback of the unit around 1 year. Maintenance is also easier because in the polyvalent heat pump case we need to maintain just one unit, just the polyvalent heat pump. In this case we have the chiller and the boiler, 2 units. And also a life cycle cost in 15 years time frame shows a saving of about 22%. It's not only a matter of electricity bill, it's also a matter of reduction of greenhouse gas emissions and reduction of primary energy consumption. The building was occupied, as I mentioned, at the end of 2011, and the energy consumption is monitored all year round because the building is controlled by a BMS system, and the real data show consistency with the analysis that we have done. But in order to understand if this technology could be applied even in a much colder city, so in a much colder climate where the use of a heat pump during all year round is not economically convenient, we've made a simulation of a similar building with the same features, same size, same envelope, same glazing, but installed in a much colder city, which is Stuttgart in Germany. This is the the energy modeling of this building in the climate of Stuttgart, and this is the temperature profile of Stuttgart, which ranges from -13 to +29 all year round. This situation makes the use of a heat pump all year round not economically convenient, because the operation of the pump with this very low temperature is not energy efficient. For this reason, it was decided to simulate a system where a hybrid system made by a polyvalent heat pump and a boiler, where the boiler is used below -5. With a gas and energy cost, the temperature at which the use of a heat pump was still convenient was calculated in -5. It means that when only heating is required below -5, the boiler is used and the heat pump is disabled. This is the simulation of a life cycle cost analysis for this situation. In this case, let's say the extra cost for the installation are even higher, because there is no saving allowed, because we have to use the boiler as well. So it exceeds 50% increase. But still, considering the operation saving, the yearly energy consumption can be reduced by around 22%, which makes the payback of the unit around slightly higher than 2 years. And still, in a 15 years time frame, we can see a life cycle cost reduction of around 17%. The reason of this saving is in this slide. If we look at the source of the heating energy used by the building, both in Milan and in a much colder city, which is Stuttgart in Germany, during the all year round, we can see that the biggest part of the heating energy, around 90% of the heating energy used by the building, comes from the heat recovery, which means it's for free. Only a small amount of that energy is coming from the heat pump, so we have to pay for that in the case of Milan, or from the heat pump from an external source, which is the boiler, in case of Stuttgart. So, just to sum up what is so far. Polyvalent heat pump technology has proved to be energy efficient and economically convenient, and also to improve the environmental impact of the building. The technology can represent a concrete help to achieve building level energy certification. In a building in Milan, the use of a polyvalent heat pump instead of a traditional system had a significant contribution in achieving a good scale in the score earned by the building in the LEED certification rating guide. The technology is very flexible and can be successfully implemented in almost the totality of commercial and institutional buildings. And this technology also has an interesting growth potential in the future, as the polyvalent heat pumps can satisfy the requirements of modern buildings in terms of efficiency, flexibility, and reduction of life cycle costs. I thank you for your attention, and if you have any questions, I would be glad to answer.
Thank you very much. Any questions? Okay, may I comment on this? And related to the previous presentation, that one of the places that these kind of pumps have great possibilities, laboratory facilities. The main reason is because we do have the all-air systems, and we do require a lot of preheat in order to control different temperatures in different rooms. It's a very well documented case for using four-pipe. We call them four-pipe heat pumps.
Four-pipe heat pumps,
Yes. It's very interesting. My question to you is about electronics. So far, I've seen many of this type of, not from your company, but from other companies as well, to suffer from the electronics and the automatic switch from the auto mode, where they have cooling and heating at the same time, and changing from the heating mode only on the cooling mode. And I believe that, have you done any research on that? I mean, do you have any hard data on
We've made a lot of research with this technology in our laboratory. We can say that a very critical factor for the success of this technology is the plant system, in which the units are exposed. A correct evaluation of the thermal inertia of the two circuits, the cooling and the heating circuit, can make the real difference between a system that operates poorly and a system which operates without any problem. The electronics, if also the plant system, or let's say the combination of unit and plant system is not correctly designed, the electronics is the first, let's say, the first part of the unit which can suffer. But let's say nowadays, according to what we have done in our laboratory, also the reliability of the electronic components that are used today, together with the correct design of the system, can make the difference.
To say more on this is, and for designers that is the most important thing is the thermal inertia of the system. If you have a machine like that and you want it to switch on and off all the time, then you're going to have a serious problem. So that means that we do have to utilize either piping systems or storage tanks in order to have large thermal inertia.
That's right.
Any other questions? Okay, thank you very much.
Thank you very much for your attention.